In the previous videos, you saw two different ways to visualize multivariable functions, that is, functions of x and y. The first way was as a surface in three-dimensional coordinates, so x, y, and z, where f of x is equal to z. So in some sense, my height of my surface for any two given values of x and y. The other way that we saw to express them was through contour diagrams, meaning we look at what curves we get, so y as a function of x when I set my multivariable function to a specific value. So my value for c is going to be the value for f of xy, and I look at what curve I get when I evaluate f equal to c. So this video is going to be purely supplementary. There's no new techniques that we're going to learn. There's no new theory that we have to discuss or any new definitions. But what I wanted to do is talk about both of those ideas at the exact same time. Let's go ahead and explore the relationship between diagrams, contour diagrams, and then also visualizing our surface in 3 dimensions. So where do these contour diagrams come from when we're looking at the surface itself? So we're going to look at a very specific example, and that's f of xy equals y squared minus x squared, or for our surface, we would say z equals y squared minus x squared. And what this looks like is kind of a Pringles chip. Okay, the way we can think of this for a surface, my x-axis is running left to right, my y-axis is running back into the screen, and my z-axis is running vertical. And I get this kind of Pringle chip. Okay, well, how does this help us with the contour diagrams? So here, what I'm going to show is that we can think of these contours as what we get with the intersection between a plane and our surface. So that yellow shape is going to be our surface in 3 dimensions, and this blue plane is going to be a plane whose z value, is equal to our value of c in our contour diagram. And what we're going to see is that this plane is going to intersect my surface, and the intersection between this plane at height c is going to recover the contour when f is equal to c. So how this picture works, on the top left, I'm slightly below the surface. On the top right, I'm slightly above the surface. The bottom left is my family of contours, so it's a contour diagram for multiple values. And on the right, it's going to be one single contour for a specific value. The red curves in every single picture are the exact same curves. Okay, so we can see them in 4 different ways. Slightly below the surface, slightly above the surface, within my entire family, and then just by itself. Okay, so the bottom 2 pictures are contour diagrams. The top 2 pictures is the intersection of my surface with some plane. Okay, in this case, I'm looking at my value of c is equal to -9. So -9 equals y squared minus x squared. That's going to be a plane at z equals -9 intersecting my surface, and I get the red contour diagram. How do I find those contours? Well, we solve for y, and what we get is y equals square root of x squared minus 9, and y equals negative square root of x squared minus 9. Here we can see I'm going to be able to get positive and negative values for y, but since I'm taking the square root, there are some values of x that are not going to have a corresponding y value. X squared minus 9 is going to have to be greater than or equal to 0. So there's no y value if I plug in 0 or -1 or 2. So I don't get a y value until I actually plug in -3 or plug in 3. Alright. Now looking at the surface, as my c value increases, my contours should get closer together. So let's look at c equals to -4. Well, here I get y equals square root of x squared minus 4, y equals negative square root of x squared minus 4, and sure enough, my curves start to move closer together. So again, I'll recover positive values for y, and negative values for y, and now my region where y is undefined is only between -2 and 2. So the region where my y values are undefined is getting smaller, i.e. my contours are moving closer. My plane is cutting higher up on the Pringle. Let's look at another one. Here we have -1 equals y squared minus x squared, and that's going to be the two equations y equals square root of x squared minus 1 and y equals negative square root of x squared minus 1. So my region where my y values are undefined is even smaller. So there's no y value when x equals 0, no y value when x equals 1/2, but when x is equal to 1, I get 1 minus 1, which is 0, so y equals 0. And this is just the same as my plane at z equals -1 intersecting my surface. Alright, now let's look at 0. This is kind of surprising. Looking at the shape, I have this nice, like, curvy shape. So it was unexpected to me that when we cut it at the plane z equals 0, I actually get two straight lines. My intersections are two straight lines. So this is why it's kind of helpful to actually try to solve for y and just plug in values. It's not always obvious what these curves are going to make. In some instances, it is very obvious. But I think there is real value to actually just plotting some points. Plug in some values for x, plug in some values for y, plug in some values for c, change the values of c, and see what we get. It's really hard to look at your surface and get exactly what the shapes are until you have a lot of practice. So before that, it's helpful to do as many calculations as possible. So when c is equal to 0, I just get two straight lines, y equals x, and y equals -x. So now what's happening, though, is as my c values become positive, we'll see that the square root is no longer going to be a problem. So let's look at y squared minus x squared equals 1. So my value of c is equal to 1. Well, I have the equations y equals the square root of x squared plus 1 and y equals negative square root of x squared plus 1. Here, any value for x is going to work because 1 plus x squared is always greater than or equal to 0. So the square root's always defined. I'm not going to have any issues whatsoever. But there are some values of y I cannot get. Since x squared plus 1 is always going to be at least 1, the smallest positive y value I can get is going to be 1, and the largest negative y value I could possibly get is going to be -1. So the values between -1 and 1 for y I'll never get. And as the plane rises higher on my Pringle, we should expect these contour diagrams to get farther and farther away, because it looks like the lobes of my surface are moving away from each other. It's getting wider and wider as I get higher, so I should expect these curves to get farther apart, and that's exactly what it looks like. So now 4 is equal to y squared minus x squared. That gives me y equals x squared plus 4, and y equals negative square root of x squared plus 4. So here, all the values between -2 and 2 I cannot get. So let's look at one more. 9 equals y squared minus x squared. I get y equals the square root of x squared plus 9, and y equals negative square root of x squared plus 9. So that means there are no x values that I can plug in to get a y value in between -3 and 3. And again, we can see that as my plane slices my Pringle, more of the shape is dipping below the plane. And so my curves are getting farther and farther apart. So whenever I look at any of these contour diagrams or any of these surfaces, I try to get a general idea of what the shape is doing, except for in very small number of cases, most of the curves will look the same. As you can hopefully see in all of these examples, we only just changed the constant, but the fact that we were always had this y squared minus x squared, or this y equals the square root of x squared plus something, this plus something only changes a little bit. It doesn't really change the shape all that much. So what I try to do is get an idea of what the basic curve looks like. Sometimes that helps if I know what the surface is. For me, I have a lot of experience graphing and drawing pictures, so I have a lot of surfaces kind of memorized, so the contour diagrams are a little easier, but that's not always the case. But again, we can kind of see all these curves have generally the same shape. What's interesting to me, at least, is how these impact where they're drawn. Is x squared negative or positive, or is y squared negative or positive? And it's helpful for me to look at the domains and ranges of my functions. So going back to what we learned in Calc 1 about the domains of functions can also be helpful for drawing these contour diagrams. So anyway, I hope this helped. Again, it's purely supplementary. If it wasn't something that was too interesting, the tools that we learned in our basic videos are all you're going to need for this class. But if you just enjoy visualizations, I hope this was something that helped.